SpaceX's Starship program represents one of the most ambitious endeavors in modern aerospace engineering, aiming to revolutionize space travel through full reusability, massive payload capacities, and the potential for interplanetary missions. The recent Flight 11, conducted on October 13, 2025, from Starbase in Texas, marked a pivotal moment, the final launch of the current iteration before a major overhaul. As detailed in various analyses, including a comprehensive review from space enthusiasts and experts, this flight showcased near perfection in execution, underscoring the program's strengths while teasing groundbreaking upgrades. In this part, we'll explore the introduction to the program and its standout highlights, drawing from the successes of Flight 11 and the promised advancements. At its core, Starship is designed to make humanity multiplanetary, a vision championed by SpaceX founder Elon Musk. Unlike traditional rockets that are mostly expendable, Starship's Super Heavy booster and upper stage ship are built for rapid reuse, potentially slashing launch costs by orders of magnitude. Flight 11 exemplified this ethos. The mission began with a reused Super Heavy booster from Flight 8, which had been refurbished at the Star Factory. Remarkably, 24 of the original Raptor engines were reintegrated after cleanup and some replacements, performing flawlessly during ascent. This reuse not only validates the program's iterative approach, but also highlights cost efficiencies. Reusing hardware reduces the need for constant new builds, a game changer for frequent launches. The ascent itself was a spectacle, a smooth liftoff into a clear evening sky, followed by precise hot stage separation. For the booster's return, SpaceX experimented with a new landing burn procedure over water, avoiding the risks of a tower catch. Instead of the previous 13-3 engine sequence, they tested a 13-5-3 transition, conserving fuel for greater liftoff performance in future versions. This innovation is crucial for Booster V3, promising more efficient operations. Meanwhile, the Starship upper stage achieved a flawless suborbital trajectory, maintaining control throughout its coast phase. A key highlight was the first planned dynamic banking maneuver at 50 kilometers altitude, allowing the ship to steer in a semicircular path rather than a straight descent. This capability is vital for future return-to-launch site missions, where the ship must navigate from over Mexico back to Texas, culminating in a 180-degree spin and engine ignition for landing. Despite these maneuvers, the ship splashed down precisely on target, demonstrating exceptional guidance systems. Looking ahead, the content previews Flight 12 as the dawn of a new chapter, with wholesale changes to the vehicle and infrastructure. The Super Heavy V3 will retain 33 engines, but upgrade to Raptor V3s, boosting thrust from 230 to 280 tons per engine. More impressively, the V3 design simplifies the engine by integrating hoses and wires into the casing, enhancing reliability and ease of production. Testing is complete, and flight-ready engines are already in rollout. The booster's length extends to house larger fuel tanks, fed by a massive internal transfer tube comparable in size to a Falcon 9, essentially a rocket within a rocket. Grid fins reduced from 4 to 3 in a T-shaped configuration, strengthened by 50% and incorporating catch pins for tower arms, aligning with Musk's philosophy of deleting unnecessary parts. The hot stage connection evolves too, replacing the heavy interstage adapter, discarded after separation in prior flights, with triangular support, beams and a reinforced methane tank dome, welded with extra steel layers for flame protection. This makes separation more sustainable and efficient. For the Starship V3, while externally similar, internal upgrades address past reliability woes, such as engine compartment explosions that damaged flaps. A redesigned fuel delivery system and Raptor V3 integration promise fewer failures, enabling 100 to 150 tons to low Earth orbit rivaling the Apollo-era Saturn V, but with full reusability, a feat once deemed impossible. Orbital docking receives its most detailed preview yet, with side-mounted adapters, male and female, for fuel transfer between ships, unlocking higher orbits and destinations like the Moon and Mars. Infrastructure supports this leap. Tower 2 introduces a flame trench and water deluge system, a taller, stronger structure, and shorter chopstick arms for faster, more stable catches. These highlights from Flight 11 and V3 upgrades illustrate Starship's potential to democratize space access, fostering innovations like large space stations, lunar bases, and beyond. As one expert noted, Starship is one of the hardest engineering challenges ever attempted, but its successes signal a transformative era. While the successes of SpaceX's Starship program, particularly Flight 11, paint a picture of relentless innovation and progress, the initiative has not been without its share of controversies. Critics, ranging from aerospace experts to environmental advocates and regulatory bodies, have raised pointed questions about the program's risks, delays, and broader implications. These debates often center on the high-stakes testing approach, environmental impacts, and the feasibility of ambitious goals like rapid reusability and interplanetary travel. Drawing from analyses of Flight 11 and previews of upcoming iterations, this part delves into the most contentious elements, highlighting how they fuel ongoing discussions in the space community. One of the most debated aspects is the program's history of explosive failures, euphemistically termed rapid unscheduled disassemblies by SpaceX. Flight 11, while successful in many respects, ended with the Starship tipping over and exploding after a soft splashdown, a controlled but dramatic conclusion. Earlier flights, such as Flight 10, saw explosions in the engine compartment that shredded control flaps, preventing a full re-entry test. Proponents argue these are invaluable learning opportunities in an iterative development process, allowing SpaceX to identify and fix flaws quickly. However, skeptics contend that the frequency of such events, nearly every early test involved some form of explosion, indicates fundamental design instabilities. Media coverage has amplified this, with headlines often sensationalizing the blasts, leading to accusations that SpaceX downplays risks. For instance, during re-entry, the ship's flaps have repeatedly shown vulnerability to melting or damage, raising concerns about the heat shield's viability for crewed missions. Critics point out that no spacecraft has ever achieved a fully reusable orbital heat shield at this scale, and persistent issues with tiles detaching or burn-throughs suggest that Starship may not be ready for human passengers anytime soon. Another flashpoint is the feasibility of key reusability features, particularly the Mechazilla Tower's chopstick arms for catching returning boosters. The content previews shorter arms for Tower 2, based on lessons from overestimating surface area needs, and a reduction in grid fins from 4 to 3, embodying Elon Musk's delete parts mantra. While this aligns with efficiency goals, experts have labeled the catching mechanism as borderline insane due to its precision requirements. Aligning a massive rocket mid-air with robotic arms demands split-second timing and could lead to catastrophic failures if miscalculated. The shift to a T-shaped fin configuration with integrated catch pins is seen by some as a smart evolution, but others worry it compromises aerodynamic stability, especially during the novel belly flop maneuver and final flip for landing. Broader skepticism surrounds rapid reusability at Starship's unprecedented scale. Unlike Falcon 9's proven drone ship landings, Starship's approach remains untested in full, with critics arguing that the program's move fast and break things ethos prioritizes speed over safety, potentially endangering future astronauts or ground personnel. In-orbit refueling, detailed in the preview with male and female docking adapters for fuel transfer, represents another highly controversial element. This technology is essential for extending Starship's range to the Moon or Mars, but it has never been demonstrated at the required scale transferring cryogenic propellants between two massive vehicles in zero gravity. Detractors describe it as ridiculously complicated and likely unworkable, citing risks like boil-off, leaks, or docking failures that could strand missions. SpaceX's role in NASA's Artemis program amplifies this debate. The company is contracted to deliver a lunar lander version of Starship, but delays have pushed timelines back by years, with no full orbital test yet achieved. Some argue that reliance on unproven refueling jeopardizes the entire moon return effort, drawing comparisons to competitors like Blue Origin's New Glenn or NASA's SLS, which have pursued more conservative paths with fewer public explosions. Environmental and regulatory concerns further ignite controversy. Frequent launches from Starbase in Boca Chica, Texas, have drawn ire from locals and wildlife advocates over noise pollution, habitat disruption, and potential chemical releases from RUDs. Splashdowns, as in Flight 11, raise questions about marine impacts, with debris potentially harming ecosystems in the Gulf of Mexico. The program's environmental footprint, consuming vast resources for fuel production and infrastructure, clashes with sustainability claims, especially as SpaceX pushes for hundreds of annual launches. Regulatory hurdles with the FAA have delayed tests, with critics accusing the agency of being too lenient, allowing rapid iterations that might overlook safety protocols. Conversely, SpaceX supporters decry these as bureaucratic roadblocks stifling innovation. Comparisons to historical programs like Apollo's Saturn V also stir debate. While Starship matches its payload capacity with reusability, detractors dismiss it as overhype, labeling the design garbage and ill-suited for lunar regolith landings, where the fine dust could cause engine damage. Broader risks, including Raptor engine inconsistencies and the need for new infrastructure like Tower 2's flame trench, underscore fears of escalating costs and timelines. As one analyst noted, Starship's extreme testing freedom afforded by private funding walks a fine line between groundbreaking and reckless, potentially setting back public trust in space exploration if major setbacks occur. These controversies highlight the polarized views on Starship, a beacon of progress for some, a high-risk gamble for others. Yet, they also drive the program's evolution, as SpaceX addresses criticisms through design tweaks. As SpaceX's Starship program transitions from the era capped by Flight 11 to the transformative upgrades previewed for Flight 12 and beyond, the implications for space exploration, commercial ventures, and humanity's long-term future are profound. Balancing the program's triumphs, such as near-perfect test executions and innovative reusability, with its controversies, including persistent failures and environmental concerns, offers a nuanced perspective. This final part examines the potential trajectories of Starship, weighing optimism against realism, and considers how addressing debates could shape its legacy in the broader context of aerospace advancement. Looking forward, the most exciting implication lies in Starship's role in enabling affordable, frequent access to space. With V3's enhanced Raptor engines delivering 280 tons of thrust each and a simplified design for mass production, the system could achieve launch cadences unimaginable with current rockets. The projected 100 to 150 tons to low Earth orbit, fully reusable, positions Starship as a successor to Saturn V, but with economics that could drop costs below $10 per kilogram compared to thousands for expendable vehicles. This democratizes space. Satellite constellations like Starlink could expand rapidly, fostering global internet access. Scientific missions to asteroids or outer planets become feasible for universities, not just governments. The in-orbit refueling via docking adapters opens doors to sustained lunar presence through NASA's Artemis and private ventures, potentially mining resources like water ice for fuel. For Mars, Starship V3 is touted as the first capable of uncrewed landings, laying groundwork for Musk's vision of a self-sustaining colony. Infrastructure like Tower 2's flame trench ensures scalability, supporting dozens of annual launches from Starbase and possibly new sites. Yet, these ambitions must contend with the controversies outlined earlier. Delays in achieving full orbital tests and reliable re-entries have already impacted timelines. NASA's lunar lander contract, originally slated for 2024, now eyes 2026 or later, prompting questions about over-reliance on SpaceX. If refueling proves as complex as critics fear, requiring up to 10 tanker launches per mission, setbacks could cascade, delaying Artemis and eroding investor confidence. Environmental pushback may intensify with increased launch frequency. While SpaceX mitigates through wildlife monitoring and cleaner methane fuel, regulatory scrutiny from the FAA could impose caps or redesigns, slowing progress. The fail-fast philosophy, while accelerating learning, as seen in fixing fuel systems post-Flight 10, risks public backlash if a major incident occurs near populated areas or during crewed flights. A balanced outlook recognizes Starship's iterative success as a strength. Flight 11's dynamic maneuvers and precise splashdown validate simulations, building toward tower catches that could enable 24-hour turnarounds, a holy grail for reusability. By reducing grid fins and integrating hot stage protections, SpaceX embodies lean engineering, potentially outpacing competitors like Blue Origin, which has yet to orbit New Glenn. However, sustainability demands transparency. Sharing more failure data could counter accusations of hype, fostering trust with regulators and the public. Collaborations, such as with NASA on heat shield tech, might accelerate resolutions to re-entry woes, blending private agility with institutional rigor. Economically, Starship could catalyze a space boom. Reusability slashes barriers for industries like space tourism, via partnerships with companies like Virgin Galactic and manufacturing in microgravity, yielding breakthroughs in pharmaceuticals or materials. Geopolitically, it bolsters U.S. leadership amid China's advancing Long March rockets, ensuring dominance in cislunar space. Yet, equity concerns arise. Will benefits trickle down or concentrate among elites? Musk's multi-planetary goal inspires, but critics argue resources might better address earthly crises like climate change, though proponents counter that space tech, like satellite monitoring, aids those efforts. In conclusion, Starship's future hinges on bridging its best attributes, innovation, power, and vision with resolutions to controversies. If SpaceX refines reliability and navigates regulations adeptly, the program could usher in an era where space is routine, not exceptional. Flight 12 will be a litmus test. Success with V3 could silence doubters, while hurdles reinforce cautions. Ultimately, as one observer put it, Starship isn't just a rocket. It's a bet on human ingenuity. Whether it soars or stumbles, its pursuit redefines what's possible, urging us to dream big while grounding ambitions in reality. Exciting times indeed lie ahead. Stay tuned for the next chapter.